Hi everyone, Josh here with the first of what I think is going to be a series of videos on things I'm personally working on in the graph space, things I think are interesting, really informal, but what I'd like to share with you today is something I've been experimenting with in a branch of Tinkerpop as we make our way toward Tinkerpop 4, and that is transporting graphs over the wire using Apache Thrift. So last year at the Global Graph Summit, I gave a talk on some of the open problems in Apache Tinkerpop and how we are thinking of approaching those problems. So one set of problems has to do with serialization formats, or with transporting graphs, storing and retrieving graphs in an application-neutral way. And there are a few formats that we use for this. One is the XML-based GraphML format. One is the JSON-based GraphSon format, which was created for Tinkerpop. There's a binary format as well. There's an adaptation of Cryo to graphs called Gryo. But all of these are specific to graphs, and most of them are also specific to Tinkerpop. And there's a desire to supplement these formats, which are very closely tied to graphs, with more general purpose formats and protocols. So what I'll show you today is Apache Thrift. Maybe in a subsequent video we'll get into Google's protocol buffers and or Apache Avro. But being able to embed graphs into applications, into services, which aren't necessarily all graph, is a useful thing to do. So with that, let's just get into the demo. Okay, so what I have for you here, maybe I should say just a little bit about Thrift first. Or maybe I won't. You get the point. It's a Thrift IDL is a language that's used for describing interfaces for services, for clients and servers to talk to each other. It has a language called Thrift IDL, which I'll show you in a moment. And then it supports a variety of protocols. We'll be looking at the T-binary protocol today. So let me just jump right into that and get into what let's give you an example of a service here. Okay, so let's create a simple service where we just want to send a graph from a client to a server, and then the server does something with it. In this case, the server will just write the graph to a file so we can load it up in Gremlin and take a look at it. So that's what this service is doing here. It has an add graph method, which just takes a property graph, and then it'll give you back some information saying, how many vertices and edges were in the graph that was just added. But the tricky part here, the part that needs some attention, is this graph type. What exactly is this graph? Property graphs historically don't have a schema, so we need to give property graphs a schema in order to do this. But we can use a fairly simple schema. So in this case, I've just taken a very simple, vertices and edges and properties data model that captures most of what we do with property graphs in practice, and turned it into a Thrift IDL. And actually there's a Dragon YAML file that was used to generate this Thrift, and maybe we can look at that too. But without getting too far down into the weeds, we've got a graph type here. A graph has a required set of vertices. It has a required set of edges. A vertex looks like this. It has an ID, which is basically just an object. It could be a string or a number. It has a label, and it has a set of properties, and that set of properties can be empty. So let's look at an edge. It's similar to a vertex. It has an ID. It has a label. It has a set of properties, but then it also has the out vertex, or the tail of the edge, and the in vertex, or the head of the edge. So let's look at properties. A property is something that has a key and it has a value. And it can have properties on top of it as well, to the extent that meta properties are supported in the application. We won't be looking at meta properties today.
But we need to look at value as well. So that's where a lot of the nuance comes in. So I based this notion of value on Tinkerpop's graph features API. I've got that here. And I think I'm looking at, so graph features is a set of features that are configurable, that can describe the features that are supported in a given graph backend or application. Here we're interested in data type features, so graph features lets you say whether strings are supported, they usually are, booleans, whether different types of lists are supported, and so on. So there's a lot of richness that can be put into a property graph data model, and there's a paper you can read if you're interested in that called Algebraic Property Graphs. But today we'll be using just a really simple property graph data model that's based on graph features. So basically just these types. And then a little bit of sophistication around how we serialize and deserialize domain-specific types. Okay, so back to the demo. What we were just looking at there was basically the atomic values, and that's these. So we have booleans. It's escaped here because boolean is a reserved word in Thrift, and some of these are reserved words in Java, so we escape them. So it's either Boolean, it's a byte, it's a double, it's a float, an integer, a long integer, or it's a string, and that's it. But then you can have complex values. So a value is either an atomic value, or it can be a list of values, which we look at as a list, or it can be a list of values that we look at as an array, basically the same thing. It's just kind of different assertions you're making about how the data can be accessed efficiently. You could have a value that's a map, you can have a value that's a set of values, and then we'll look at this thing later, the serialized value. That's how we encapsulate domain-specific objects. I think I've said enough about that. Let's go back and look at the service IDL again. And so we've looked at property graphs, the IDL. Just briefly, I will show you the dragon model that's generated from. So this is the same thing. It's just written in a YAML format that's very expressive with respect to types and annotations on types. And this can be used to generate a variety of generate schemas into a variety of languages. So the application I use to do that is called Dragon. There's a series of presentations on the category theory and applications meetup group called How to Build a Dragon, if you're interested in that. But just a footnote that when we want to do the same thing in Protobuf or in Avro, it's going to be relatively straightforward because we have this model that can generate those language-specific schemas in a consistent way. Okay, so we talked about elements and graphs and so on. We talked about values. Talked about graph features. Okay, so let's get into the actual running of the demo. I've got a little Readme here that tells you what to do. By the way, if you want to check out this code, it's in a branch of Tinkerpop that has this name, Tinkerpop 2563-language. If you just select from the branches on the Tinkerpop GitHub page, just look for the one that ends in language. Okay, so, and I don't think I'll talk too much about, again, like how the thrift is generated. The Java code that we'll be using, some of it is generated from the thrift files. So we have Java classes that are generated from the property graphs IDL that we saw, and then we have other Java classes that are generated from the service description itself. And I can briefly look at those. So Java Here's the property graphs data model, per thrift. And it has lots of thrift specific stuff in it, but basically that encapsulates that set of vertices and that set of edges. Atomic value has all these different alternatives for a value, and so on. And then the generated code from the service encapsulates the service and the operation that you can do with the service. In this case, is adding a graph. So let's look at the server. So this is going to expose that method we saw that lets you add a graph. And the important thing here is just that it's, where is it? Yeah, example service is the service that you saw in the IDL, and then add graph handler is what actually adds the graph. And we'll look at that in just a moment. The client has a little more in it in terms of graphs. So the client is going to make a call to the server, sending a graph that it constructs in this way. So you can imagine it sending any kind of graph, but in this case it's creating the Tinkerbop classic graph and then adding some additional stuff into it, and we'll go back and look at that stuff. But then the handler here is what catches the graph that's sent by the client and does something with it. So it's creating, in this case, a new Tinker graph, and it's going to decode it from the thrift objects that are sent over the wire, and put it into the Tinker graph instance. And then we do a few things here to inspect the graph and see that we got the correct graph. It writes it to a file, a graph JSON or graphson file. So let's maybe just run the demo. So this is the server. Start up the server in one JVM, and then we'll start the client in a different JVM. And this is going to make our call to the server, sending that small toy graph that we construct at runtime. Okay, it looks like it was successful, so that means it should have written a file, graphson file here, and that's this. You can see it's mostly just a Tinkerbop classic graph. It also has some other stuff in it. Awesomeness is there. And we can also load it up in Gremlin. So let me just paste this in. Reading in the graphson file, and then we can see like whatever we want to do. And you can see that's the Tinkerbop classic graph with some additional things in it. So that worked. We sent a graph over the wire. Now let's go look at the other things that we added to the graph, because that's interesting and important as well. So a lot of graph implementations will let you put domain-specific objects in the graph as property values. In this case, we are adding a property called livesin that has a value which is a bounding box object. As an instance of this class, it has a couple of other objects in it called Geopoints. So it's a bounding box defined by a northwest point and a southwest point. And this is not part of the property graphs data model, obviously. So we need to account for this in some way, and the way that we do that is by giving bounding box an encoder or an encoding. So this here is creating a JSON-based encoding that will take an instance of bounding box, turn it into a JSON blob, and conversely, we'll take a JSON blob and turn it back into a bounding box. And you'll need one of these for each language in which you want to use bounding boxes. So if you only need Java, then all you need is this code here. It's very simple. It just uses Jackson object mapper to serialize the object and then to deserialize it again. If you're using Python, you need something Python specific to receive that bounding box object and turn it into something native on the receiving end, or to create it in the first place. That works like this. So this is where I put some domain specific things. You have Geopoint, you have bounding box, and then you have this application that adds the encodings that are needed for working with bounding box and Geopoints. And that is just something which is basically a map that links a Java class with a string that identifies the encoding with the encoder itself that you just saw. So when you get a serialized value over the wire, it will have an identifier associated with it that's the name of the encoding, so you know which encoder to use, and that gives you back your object. That's all part of this class here called graph encoding, which will say take a native atomic value and turn it into a thrift object for sending over the wire, and on the other hand, we'll take a thrift object and turn it into a native value, and then the general purpose version of that is we'll take any object, and then it'll do various things. It'll check if it's an array. It'll turn it into a thrift compatible array, list, and so on. And this is where the encodings come in. So if it's not any of those things, you will look it up by class in this case and see is there an encoding that can be used to turn this into something thrift compatible. So hopefully that doesn't make all of this look too complicated. It's really not very complicated. And tools like Dragon will help with these. I tried not to make this demo depend too much on Dragon because it's not open source. So let's go back and look at this again. We'll say let's look for Josh. Here are my properties. I've got a name and an age, and I added awesomeness 1.0. What that means exactly depends on your schema, your semantics of the graph. If it's a scale of 1 to 10, I'm not very awesome. If it's 0 to 1, I'm pretty awesome. So that is all domain-specific semantics. There is no schema in this case that describes what awesomeness is. But so let's look at lives in. That is this. That gives you the bounding box. So that went over the wire okay. When we're serializing this graph to GraphSon, that code doesn't know what to do with bounding box other than to turn it into a map. That's a reasonable thing to do if you don't have any domain-specific way of encoding the bounding box. In the future, you could potentially use the same encoding in GraphSon as we just used for Thrift, or a very similar encoding that's basically based on the same mapping. but just to prove that it actually is an object of the type bounding box here, in add graph handler, when we receive the graph, we're going through and looking into the properties to find that lives in value, and I print it out here. It is in fact an instance of bounding box. So it was a Java bounding box on the client side. It is reconstituted to a bounding box on the server side. And that's probably about enough for today. So maybe I'll just show you serialized value. That is, or I'll actually show it to you in the Thrift. So this is the trick by which we send domain-specific objects over the wire. It's very similar to a type called any in protocol buffers that gives you a URL for the encoding and then some data. In this case, we're sending the data as a string. For a more efficient representation, you might want to send it as a byte array, but this will do for now. So hopefully you were able to appreciate the flow of things, sending graphs over Thrift. And once again, doing the same thing in protobuf, doing the same thing in Avro ought to be relatively similar, and you ought to be able to do the same sort of thing in each Gremlin language variant with a small amount of language-specific code.